Hello everyone, let's move on to the next session in lipid metabolism. So today we are going to be looking at cholesterol. So we'll look at how is cholesterol synthesized, how is it degraded, and what are the special products that are formed from cholesterol. The disorders associated with cholesterol, we will be looking at it after lipoprotein class is over. So it comes under a separate session. So cholesterol, chole means bile and steros is solid. Usually anything ending with "ol" refers to alcohol. So that is how it's got the name cholesterol. So this is a 27 carbon compound and this ring structure is called as cyclopentanoperhydrophenanthrene ring. So it is one of the most important sterol in animal tissues, in animals. So if you take a 70 kg man, approximately about 140 gram of cholesterol will be present. Of this, I think around 30 grams will be present in brain, maybe 30 grams in adipose tissue and another 30 in muscles. So it has a rigid membrane structure and this has a ring structure. So location, it's abundantly found in those tissues which synthesize steroid hormones. So mainly in adrenal cortex, ovaries, testes. So dietary sources, as I mentioned previously, I think during digestion and absorption, that vegetarian sources, that is anything from vegetable origin will not have any cholesterol because they synthesize phytosterols and not cholesterol. So whatever cholesterol we get from diet has to be only through animal sources. So liver, meat, egg yolk, milk products, all these will give us cholesterol. Again, per se, people generally have this notion that cholesterol is bad, but it is not actually bad. It is something that is essential. So if you're not producing enough cholesterol, then lot of other activities will be affected. Synthesis of hormones, synthesis of vitamin D, absorption of dietary lipids, all these get affected if cholesterol is not there. So cholesterol is good, is necessary, but it's just that the amount of cholesterol that is present is what defines good and bad. So when it increases more than what is required, it can become bad. So if you look at the turnover in a day, it is about 1 gram per day. We can get about 50% from synthesis and maybe another 50% from the diet. So if you are on a very high cholesterol diet, then the amount that you absorb will be less. If you are on a low cholesterol diet, amount that you absorb will be higher. And again, this also depends, this will decide how much of synthesis needs to happen. So it's undergoes fecal excretion, that is from bile reaches intestines and has to be excreted. So it's acted upon by intestinal bacteria and converted to neutral sterols. Coming to the synthesis, de novo synthesis of cholesterol. So Conrad got a Nobel Prize for showing that cholesterol entire molecule is made up of acetyl-CoA, that is the acetyl-CoA units that are used for synthesis of the cholesterol molecule. So the amount of synthesis, as I mentioned, depends on dietary intake. So if you are taking a higher dietary intake, then synthesis will be reduced. So there will be a feedback, that is an inhibition on synthesis. all nucleated cells can synthesize cholesterol, including arterial walls, the cells in arterial walls. Everywhere cholesterol can be synthesized, but the amount of synthesis is higher in liver, adrenal cortex, intestine, ovaries and testes, skin, arterial walls, etc. Slightly lower amount of synthesis happens in muscle and adipose tissue. Within the cell, location mainly happens in the cytoplasm, whereas partly in the endoplasmic reticulum also. We will look at which enzyme is present in endoplasmic reticulum. So coming to the actual synthesis, starting material is acetyl-CoA, as I mentioned. So normally acetyl-CoA is produced in the mitochondria. So which are the pathways that lead to formation of acetyl-CoA? Mainly from glycolysis we get pyruvate, and from pyruvate oxidative decarboxylation we get acetyl-CoA. So it can be one of the major sources. Oxidation of fatty acids. We have discussed about beta oxidation just previously. So oxidation of fatty acids will also lead to formation of acetyl-CoA. Then degradation of the carbon skeleton in some of the amino acids, glucogenic amino acids, and degradation of ketone bodies. These are the various pathways from which we get acetyl-CoA. So now synthesis of acetyl-CoA is happening in the mitochondria, and cholesterol synthesis will happen in the cytosol. So this acetyl-CoA has to be transported from mitochondria into the cytosol. So let's look at how this happens. This requires the acetyl-CoA shuttle or citrate shuttle. So in the mitochondria, first step in TCA cycle is condensation of oxaloacetate with acetyl-CoA to form citrate. So this citrate can exit the mitochondria. There is a tricarboxylic acid transporter. There is a transporter for tricarboxylic acid. So citrate exits through this transporter, comes into the cytosol. In the cytosol, it's acted upon by citrate lyase, which breaks it down to give acetyl-CoA and oxaloacetate. Now this oxaloacetate has to be sent back into the mitochondria, otherwise there will be depletion of oxaloacetate in the mitochondria. So oxaloacetate can get reduced to malate. Malate dehydrogenase is the enzyme. So oxaloacetate forms malate. Malate by malic enzyme will synthesize pyruvate, and pyruvate has a transporter. So pyruvate can enter into the mitochondria, and there it can undergo carboxylation to form oxaloacetate. So this is the citrate shuttle for transporting acetyl-CoA from mitochondria into the cytosol. The synthesis of cholesterol, we will be looking at it as 4 steps. The first stage is up to formation of mevalonate. Your university RGUHS expects you to know the proper steps of synthesis till formation of mevalonate. After that, exact steps need not be memorized. You can just write what are the compounds that are formed, and maybe even enzymes or coenzymes are not that important. Stage 2 is formation of isoprenoid units. These are the 5 carbon units. Isoprenoid 5 carbon units activated. Stage 3 is formation of squalene, which is the first cyclical form that is produced. And next is conversion of squalene to cholesterol, that is a 27 carbon compound. So when we spoke about ketone body synthesis, I did mention that this shares 2 steps with cholesterol synthesis also. So it is the same steps, only difference was ketone body synthesis was happening in the mitochondria, whereas cholesterol synthesis is happening in the cytosol. So first step is condensation of two molecules of acetyl-CoA to form aceto-acetyl-CoA. Enzyme is aceto-acetyl-CoA synthase or thiolase. So next, again condensation of aceto-acetyl-CoA with another molecule of acetyl-CoA to form HMG-CoA. Enzyme is HMG-CoA synthase. So this is a 6-carbon compound HMG-CoA, hydroxymethyl glutarate CoA. So these two steps are common to both ketone body synthesis and cholesterol synthesis. After this, the next step, in ketone body synthesis we saw there was a breakdown of this HMG-CoA to give acetoacetate, whereas here HMG-CoA will undergo a reduction by the enzyme HMG-CoA reductase. This step is the rate limiting step. It is also the committed step for cholesterol synthesis. This step is happening in the endoplasmic reticulum. So HMG-CoA is reduced to form mevalonate, and this requires 2 molecules of NADPH and it forms mevalonate. This is the stage 1. Forming of mevalonate is stage 1 in cholesterol synthesis. After that, mevalonate will undergo successive phosphorylations, 3 phosphorylation steps to form 3-phospho-5-pyrophosphomevalonate, which is still a 6-carbon compound, but this has 3 phosphate groups in it. So there are 3 successive kinase reactions, 3 successive phosphorylations to form 3-phospho-5-pyrophosphomevalonate. Next step is a decarboxylation. From a 6-carbon compound, it now forms a 5-carbon compound, isopentenyl pyrophosphate. This is the isoprenoid unit and this contains 5 carbon atoms. Isopentenyl pyrophosphate will undergo isomerization to form dimethyl allyl pyrophosphate. Okay. So it can form dimethyl allyl pyrophosphate. In the next step, there is condensation of 2-dimethyl allyl pyrophosphate to form geranyl pyrophosphate, which is a 10-carbon compound. Dimethyl allyl pyrophosphate is a 5-carbon compound. So condensation of 2-dimethyl allyl pyrophosphate will lead to formation of geranyl pyrophosphate. Next, there is again transferring of 1 isopentenyl pyrophosphate to this. So it is 10 plus 5 combining to form farnesyl pyrophosphate, which is a 15-carbon compound. In the next step, 2 molecules of farnesyl pyrophosphate will condense to form squalene, which is the first cyclical structure and it has 30 carbon atoms in it. So this is the next stage. Stage 1 was formation of mevalonate. Stage 2 was formation of isoprenoid units. Stage 3 formation of squalene. Now from squalene it forms lanosterol, zymosterol and then desmosterol, and ultimately it will form cholesterol, which is a 27-carbon compound. So for elucidating the steps of cholesterol synthesis, Nobel Prize was given to John Comforth and Vladimir Prelog. So overall reaction, this requires 18 acetyl-CoA and 36 ATP and 16 NADPH for synthesis of 1 molecule of cholesterol. So what happens once cholesterol is synthesized? This free cholesterol will undergo esterification at the hydroxyl group present at position 3. The hydroxyl group here undergoes esterification to form cholesterol ester. Enzyme is acyl-CoA cholesterol acyl transferase. And this cholesterol ester is now forms part of VLDL and is transported through VLDL to other tissues. Or whatever cholesterol that has been brought back to the liver, reverse transport of cholesterol happened and needs to be excreted. This is secreted into the intestine via the bile by the formation of bile acid. So, in one of the later slides we look at how are bile acids synthesized. So, cholesterol that is formed has two fates. One is it will be transported to all tissues which will take up cholesterol for their requirements, and excretion of cholesterol happens through bile as bile acids. Inhibition of HMG-CoA reductase, that was the rate limiting step. So, if we want to either increase or decrease the cholesterol synthesis, we have to target HMG-CoA reductase. So, to reduce cholesterol synthesis, certain drugs which are commonly called as statins are used. They have the side chain, that is mevalonate, has a resemblance to the side chain that is present in cholesterol, and because of this there will be a competitive inhibition. So, there are many studies which have shown that there is decrease in blood cholesterol and decrease in the risk for cardiovascular disorders on starting statins. So, this has become a standard of care to start statins for people who have high cholesterol. Now, looking at regulation of cholesterol, HMG-CoA reductase is the regulatory enzyme. So, there is a feedback inhibition. When there is excessive cholesterol, cholesterol itself will inhibit formation of more cholesterol. So, this is a feedback inhibition, one type of allosteric regulation. There is also a covalent modification, that is HMG-CoA reductase can undergo phosphorylation, dephosphorylation. So, it is active on dephosphorylation and inactive on phosphorylation. So, insulin will increase cholesterol synthesis, whereas glucagon will decrease cholesterol synthesis. In the long term also, insulin and T3, T4 hormones will increase the synthesis of the enzyme itself at the gene level, and they will increase cholesterol synthesis. Cortisol will decrease cholesterol synthesis. So, this is regulation, feedback inhibition, then covalent modification, that is for HMG-CoA reductase, and at the level of gene increase by insulin and thyroid hormones, decrease by cortisol. So, we will look at what is the fate of cholesterol once it is formed, what are the special products that can be produced from it. So, one, it can be degradation to form bile acids and bile salts, or used for synthesis of vitamin D or for synthesis of steroid hormones. Now, how do we form bile acids? We know that cholesterol is sparingly soluble in water, and if it is esterified at this position, there is a fatty acid attached here, then it becomes even more insoluble. So, to increase solubility, we can increase more hydroxyl groups, and that will help in the solubility. So, cholesterol is converted to cholic acid by a hydroxylase reaction. So, cholesterol by 7 alpha hydroxylase will form 7 hydroxy cholesterol, and from this we can form cholic acid and Kennedy-oxycholic acid. These two are the primary bile acids, cholic acid and Kennedy-oxycholic acid. Now, this can undergo another step of conjugation with either glycine or taurine to form glycocholic acid or taurocholic acid toro or glycocanedioxycholic acid. Okay. This is a conjugation reaction with the amino acids glycine and taurine. Now these will be acted upon by intestinal bacteria and converted to deoxycholic acid and lithocholic acid. These are the secondary bile acids. In the intestine, acted upon by intestinal bacteria and converted to the secondary bile acids. So as we can see here, there is lot of there is recirculation between the intestine and the liver, and whatever has been acted upon by intestinal bacteria is also reabsorbed, goes to the liver, again excreted through bile, comes back into the intestine. So there is some amount of transport happening there itself, enterohepatic recirculation that is happening. So ultimately we excrete about 0.5 gram of cholesterol per day. Now if there is increased excretion of these bile acids, then it can tend to form stones. Normally same amount of phospholipids also will be excreted, so that it helps to keep whatever bile acids are there in solution. So if there is less bile acids that are being secreted, then leads to formation of gallstones, and this in turn can lead to obstructive jaundice. So treatment here is giving canediol, which can dissolve the gallstone that is there, but requires a very long time, or surgical excision of the gallbladder can be done. Next is formation of cholesterol. So from cholesterol we get 7-dehydrocholesterol, which is present in the skin, and when UV rays fall on the skin, it converts the 7-dehydrocholesterol into cholecalciferol. This cholecalciferol undergoes hydroxylation at 25th position in the liver to form 25-hydroxycholecalciferol. Next, there is another hydroxylation that is happening in the kidney at position 1. So now it forms 125-dihydroxycholecalciferol or vitamin D, which is the active form of vitamin D. The next special products that are formed from cholesterol are the steroid hormones. So cholesterol is the precursor for synthesis of glucocorticoids, mineralocorticoids, progestins, androgens, estrogens. So all these will be synthesized from cholesterol. So as I mentioned, cholesterol is very essential for the body because we get various hormones from it, we get vitamin D from it, and we are also forming bile acids. Cholesterol is a part of the cell membrane. So per se cholesterol is not bad, but it's only dependent on how much of cholesterol is present. So I think that brings us to the end of today's session. So I will see you in class. I hope you listen to this material and come prepared for the class. See you. Thank you.